Welcome back. In this video, we're gonna try to find all the polynomials that would satisfy or will have to satisfy p of x is p of x plus 2, p of 0 is 1. Okay, so here we remember that we can write a polynomial in its general form in this way. So this is one way of writing the polynomial. Note that these powers here are in n. Okay, so here we accept that 0 is in n. Okay, and we start from 0. Okay, because we can write it in this manner: a0 plus a1x plus a2x squared, and etc. until the last one, which is a sub n x to the power n. Okay, so here this is the general form, and we want to find the form of these polynomials that would satisfy this let's say this equation, okay, or this condition here. We can solve this one in many different ways. There are easy ways and longer and harder ways, but for us we want to find the easiest way to do so. Okay, I believe one easier way is we can start with some simple forms of the polynomials. We're gonna start with the constant polynomial. Okay, so let's say that we have p of x is a sub 0, the constant polynomial, and we're gonna see if this one satisfies these conditions. So if we see here that we have p of x is p of x plus 2. This is satisfied since this is a constant polynomial, and we need to have this condition here. So we're gonna enforce this a0 to satisfy this one here. Therefore, we need to have p of 0 is 1. This will give us 1 is a0, and therefore we can just set p of x is 1. So we see that this constant polynomial p of x equals 1 is a solution, is satisfying all the conditions here. Okay, are there any other solutions? We can check. We can start by looking for higher powers. So this is one way of solving this problem. Okay, the other ways are either use this fact that p of x is p of x plus 2, or use the general form and try to simplify it and use identification to solve it. Okay, but for us we're gonna proceed in this manner here. Now let's say that we have a p of x is a sub 0 plus a1x. So this is a polynomial of degree or order 1. Okay, so first we set this condition: p of 0 is 1. This will give us p of 0 is 1. That means a0 is 1, and therefore p of x is just 1 plus a1x. Okay, so this is the first condition. The second condition is that p of x is p of x plus 2. So let's set this one and see the general term or the general form of this solution. Once we do so, we have 1 plus a1x is, so here we have 1 plus a1 x plus 2. This is 1 plus 2a1 plus a1x. Okay, so here we have we can simplify here. This one will go with this one, and we have 2a1 is 0. That means a1 is 0. Therefore, again we get p of x is 1. Okay, so if we set the polynomial as the solution as a polynomial of degree 1, we see that we get back to the constant polynomial. Therefore, we believe that the only solution is the constant polynomial, which is this one here, given by p of x is 1. How can we proceed and say that the result is true in general? We can use induction. Okay, So we can use induction and assume that for all n bigger than 1, an is 0. And we need to prove that an plus 1 is 0. Okay, that means the next term is also 0. Okay, and therefore we can solve this binomial. Since we know that in this case, we know that the an are zeros, are equal to 0. We want to prove that an plus 1 is 0. Okay? How can we do that? We have to use the fact here, this one here. Okay? So we have that p of x in this case is going to be written, assume that it can be written in this manner. So it's a sub k, x to the power k, k going from 0 to n plus 1. Okay? Assume that we can write it in this manner. Okay? But this is just, if we equate it with the other condition, it's going to be the sum ak x plus 2 to the power k with k going from 0 to n plus 1. Okay? But we have one more condition here. We know that all this case, k going from 1, in fact, not from 0, from 1. K going from 1. Okay? We know that this is 0, so we're going to go to n. So this one will be simply an plus 1 x to the power n plus 1. It's going to be an plus 1 x plus 2 to the power n plus 1. Okay, we have used the condition or the induction hypothesis that all the a sub k's with k going from 1 to n are zeros, are equal to 0. So once we do that, here we can expand a bit here. So here we see that if we try and expand this one here, okay, so this one we can use the binomial theorem to express the general term. Okay, so here we have an plus 1, the sum, let's say k going from 0 to n plus 1 of n plus 1 k x to the power k 2 to the power n minus k. Okay, in particular, when k is n plus 1, sorry, when k is n plus 1, so here, and I need to add 1 here, 2 to n plus 1 minus k. So when k is n plus 1, we're going to have an plus 1 x to the power n plus 1 is, so an plus 1, it's going to be, this is just 1, and this is x to the power n plus 1. Okay? Plus when k is n. When k is n, so we're going to have an plus 1 x to the power n, and this is going to be it's going to be 1. So when k is n, so it's going to be 2, in fact. It's going to be 2an plus 1 x to the power n plus other terms. So here, this first term here, an plus 1 will go with this one here, and we have this one here is going to be 0. Okay? So we're going to have 2an plus 1 is 0. That means an plus 1 is 0. And that's what we have to prove. And this means that all the terms are 0 except for the first one, which is the constant term, which is a0, which is 1. Therefore, p of x is 1 is the only solution for this polynomial equation. Okay, so this is one way. Okay, we have to clean it a bit. We have to go back and rewrite everything nicely, but I think you get the general idea. Okay, what we mean when we say that. So this is a induction-based proof for this result. Okay, there are many other ways, as I said earlier, but this is enough for now.